Hi, NA Physics, it's Mr. Neff. Hey, today I want to talk about line spectra. But before I do, what's worse than raining cats and dogs? I'll tell you about that at the end of the video. We saw that whenever you have a solid object and you heat it up, it's going to vibrate with the whole spectrum of frequencies. It's going to now as you heat it up more and more, the frequency that the ones on the outside, the ones that are most plentiful, are going to produce. That frequency is going to shift. It's going to go from there to there. You'd expect it to just climb, but it actually climbs and comes back, showing that more energy is actually coming from higher frequencies. But you got, between some limits, you got all the frequencies, wavelengths, energies represented there. Well, that's what you see with solids, but with gases, that doesn't happen. With gases, you're going to see just these very particular frequencies. You'll have ones that are in the ultraviolet range. You'll have ones that are in the visible range, like these. You'll have ones that are in the infrared range. But you're not going to have a whole continuous spectrum of frequencies being emitted. If you excite a gas, you're just going to get particular frequencies. Now, the difference between those two is the topic of much of this unit, and I want to hit more upon that right now. Now, before that was well understood, it was quantified. It was known where those bright lines were going to be. In fact, if you would take those bright lines and put them along a spectrum, you would see that they kind of appear in a few little bunches, real close together, and then they get spread out as they go, but distinct little bunches. They gave the bunches names, and they called the ones that were ultraviolet light, they called those the Lyman series, ultraviolet light, high energy stuff. And it turns out that you could predict what wavelength you'd get with this thing called the Rydberg equation. Again, before they ever knew where this was coming from, they could say, well, this is what the series looks like. And you can say that if I gave you some mathematical data, you'd be able to make a model of that, an equation of that too. Seems like it shows up with a 1 right here, and then from 1 it goes 2, 3, 4, and higher. Now, there were ones that were visible light, and they were called the Balmer series, named after another scientist. And it was a constant, a Rydberg constant, times this these subtraction of these two fractions, but we would have a 4 there, or better said, a 2 squared. The Paschen series, which were the group that were in the infrared, lesser energy, but still there, 3, and then you'd count up 4, 5, 6 for what would go in this second one. Okay. Now, you're in a privileged spot where you're in the 21st century, and you can look back and you can say, oh, I can see where that's coming from. Maybe you can't, maybe you can, but all that to say, we're in a privileged spot where the scientists a long time ago didn't have our privilege. It took a long time to understand what was going on. We had different models of the atom, from Dalton's billiard ball model, which I know sometimes we laugh at, but in the end, he had this idea that an atom is this smallest indivisible particle. Now, we've refined that a little bit, but that was a good start. To Thomson, who had the plum pudding model, an idea that an atom was a lot of positive stuff, that would be the pudding, and then the negatives were the plums that were inserted inside of there. That an atom, that we laugh at the plum pudding model today too. We shouldn't, because there were some great points there, that the electrons are negatively charged and that the atoms are neutrally charged. Great stuff. And then we had Rutherford, and he came along with this planetary model, and you've seen this a million times. The idea that Rutherford had is, hey, it's not full of pudding. It's mostly empty. That there's a real small nucleus, and then there are real little things that are orbiting around, and for the most part, it's empty space. That's what the gold foil experiment, that's very, very famous, told us. Those were great, and those got us going, but the problem with them, the planetary model, the ultimate one there, was that if it really were a planetary model, well, the electrons would collapse into the nucleus because orbiting electrons are vibrating charges, and vibrating charges are going to produce electromagnetic radiation, and consequently those electrons are going to lose their energy. At some point then, the atom is going to collapse, and you would think that would have happened before now, but we still have atoms here today. And so it's what's going on there? Why don't we have that atom collapsing? Well, along came Niels Bohr. And Niels Bohr came up with a model of the atom that I know that you've been taught to turn your nose up at this, but you really shouldn't either. There are some issues with it, but it actually works great for a lot of atoms that have low atomic number. And we're going to primarily be focusing on hydrogen, and so it's going to work really, very well for us. Bohr said that there were energy levels. He called them orbits or shells. He gave them letter names, K, L, M, N, and so forth as you go up. And there are number names, 1, 2, 3, 4. That number, 1, 2, 3, 4, is known as the quantum number of that state. Now, the point that Bohr made, and where this goes a little off the rails, is the atom is, the electron is only able to exist in that energy level and nowhere outside of it. Now, we know that that's more of the highest probability of where the electron was. But we're still going to go with it for now. We're going to say that where the electrons are, they're going to be in state 1 or they're going to be in state 2, or 3 or 4 or 5, but not in between, not at 2.5, not at 0.6. No, they're going to be in those energy levels. Now, they can move around in those energy levels. If light comes in here and it's the right frequency, the right color, the right wavelength, the right energy, then the electron could actually absorb that light. But if it's not the right color, it will just let it pass right through. Whenever you have an atom that is, or an electron that is absorbing energy, it goes to a higher energy level. And so here we have, and I don't really like how this starts in the nucleus, but maybe it starts there and it goes to a higher energy level. Well, when that happens, as you're absorbing the energy, so in came a photon with just the perfect amount of energy because it had the perfect frequency for that transition, and it went up to another energy level. You can also spit that energy out. And if you did that, if you went from the exact same starting and ending points just in reverse, well, the photon that you'd spit out would be exactly the same frequency, energy, wavelength, and all of that. So there's certain frequencies that the atom likes. The amount of energy that the photon would carry away would be the difference in the energy levels. So here there's a certain energy level and an amount of energy in that energy level, energy 1, and I'll give you a way to calculate that in the future. And there's an amount of energy final, and if I would subtract those two, then I would be able to have the difference of energy, and that's the energy of the photon, HF. Now, you might think, well, why isn't that final minus initial? It does seem backwards, doesn't it? You're going to see that as we go through this, we're always comparing to this electron that's free, and everything's compared to that. And so you're going to see that this energy is a very negative energy. This energy is a negative energy, but not as negative. More on that coming up in the future. So it's very important to realize that the energy of the emitted photons is going to match exactly the energy of the absorbed photons. Match them in energy, match them in wavelength, match them in frequency, match them all around. Sometimes we draw pictures like the one I just had, but it's very popular to draw this simplified version, and this is an energy level diagram. Energy level diagram is going to basically just show them like shelves on a bookcase. They're really portions of circles, but they're just showing them like shelves on a bookcase. Now, you can see something here that all of these are showing releasing energy. You're going from an energy level down to a lower one, and so this is showing that energy is being emitted. Turns out that if you took a sample of hydrogen gas and you passed some electricity through it, this is exactly the way it would look. You would get this red line, and you would get this bluish line, and this darker blue line, and these purple lines, just like that. Well, you see this, that the reason that you're getting those is because that's the energy associated with going from energy level 3 down to energy level 2, and energy level 4 down to energy level 2, and 5 down to 2, and 6 down to 2. Now you might say, what about down to 1? Well, all the way down to 1 would be a really far drop, and so that releases a ton of energy. Remember those Lyman lines that we talked about before, that they're in the UV range? So you can't, they're not, the UVs aren't pictured here because this is a picture of visible light. And so when you see the picture, unless it's a representation, if you see a picture, they're going to be ones that we're dropping into 2, because that's the amount, that's the transition that corresponds with the amount of energy to give the right wavelength to see. Now, to me, a neat thing is the same, as I said a second ago, the same frequencies that you absorb are also the frequencies that you will emit. And so if you took some, say you took some white light, and you shine, say this was a hydrogen, and you shine this white light in here, right? So here comes some white light. Well, most of that light would just pass right on through, because most of that light's not the right frequency. But you see, the red will be sucked out, and guess what? It's exactly the same kind of red as before. The blue will be gone, that darker blue, these purples, they'll be gone out of there. Why? Because they give the perfect amount of energy to go up to the next energy level. And so there you go. Now every atom's going to have a little bit different group of lines, because every atom has a little bit different energy levels. And so that almost becomes the signature where you can say, oh, there's the lines, either present or missing, and you'll say, okay, then this must be boron, or this must be hydrogen, or something like this. Okay. Now, a quick little example here. I say, only photons who exactly match a transition between 2 energy levels will be absorbed or emitted. No other frequencies will be. And so check this out. I have a hypothetical atom that has energy states as shown here. And so, as I said, it has an energy in -1, -2, -3, -14. Remember, an electron here compared to an electron out here that is free, that is off the atom. Well, you see this -14 means that I would need to add 14 electron volts to shoot this thing off the atom. Here I'd only have to add 3 electron volts to shoot this off. 2 electron volts, 1 electron volt. See? So now we say, which of the following is a transition that the electron in this atom could not make? Now I'd like you to pause this for a second, and I'd like you to determine which one of those an electron could not make. Okay, and we're back. And could an electron absorb 1 electron volt? It sure could. If a photon that was carrying 1 electron volt came in, it could absorb it. It could shoot you from -2 to -1. How about 2? Well, sure you could. You could go from 3 to -1. So that could work. B could work. How about C, emitting 10? Well, you can look hard, but you're not going to be able to see a transition of 10. So that's not going to be there. Emitting 11? Oh yeah, you could emit 11. You want to see emitting 11? That would be right here. See, emitting, so we're going down, going to a lower energy level. And so this is the wrong one, so that's why we're picking it. Okay, we're going to continue our talk on the second video of the line spectra, so tune in for that. But remember, what's worse than raining cats and dogs? Well, of course, hailing taxicabs.